Welcome back. Let's talk about Hess's law. So in class the other day and in the previous video, we were talking about working with thermochemical equations, and we said there were three guidelines. That the amount of heat that's given off is proportional to the amount of product or reactant that you have reacting, that the value for delta H changes sign when the reaction is reversed, and that the value for delta H will have the same value regardless of the number of steps. So we're going to put that third one and the other two to use today. So if we look at and talk about what this third guideline is telling us, and we look at it pictorially or graphically, let's say I have my reactants and they have a particular enthalpy. And I also have my products and they have a particular enthalpy. The difference in enthalpy between the reactants and products is going to always be the same because it depends on the chemical nature of the reactants and products, the bonds, the state. It depends on what's going on in those compounds. And that is going to stay the same regardless of whether I'm actually able to make this chemical reaction happen in one step, or if I have to break this process down and have it happen in 2 or 3 smaller steps where I kind of get closer and closer to my target product, or if I end up with a situation where I make something entirely different with maybe even a higher energy, and then I'm able to make my product. The overall change in energy is always going to be the same. And this is a reflection of the fact that enthalpy is a state function. And this can be an incredibly useful fact to exploit because sometimes a chemical reaction doesn't actually happen in one step, or we can't even make the process go directly from reactants to products. Either we get extra stuff made along the way, there are side reactions, maybe things might be hazardous, or maybe we want to predict the amount of energy that's going to be associated with the chemical process so we can plan accordingly. And so let's take a look at an example where this is indeed the case. So if I want to calculate the enthalpy of a reaction for graphite reacting with 1/2 mole of oxygen to form carbon monoxide, I can't do this directly. It turns out when you try to run this reaction, you get a mixture of carbon monoxide and carbon dioxide forms, so you have no way to actually measure it. Instead, we're going to have to predict it from 2 things we can measure. So we can react graphite with oxygen to form carbon dioxide. And we can measure the heat transfer associated with that as 393.5 kilojoules of heat being given off, thus the negative sign. And this is for the reaction as written. Similarly, I can react carbon monoxide with oxygen to make carbon dioxide. And I can measure the amount of heat that's given off for that process. So if I take these 2 equations and combine them, I can figure out what happens overall. Graphically, what I've got going on is I have my graphite and my oxygen, and I know its enthalpy and energy relative to carbon dioxide, which is down here, is a difference of negative 393.5. And I know that carbon monoxide and oxygen have an energy difference that is 283.0 kilojoules per mole, reaction as written. And so what I want to find is just this difference in energy here. And so there's a way to manipulate these equations. Well, what we're going to do is we're going to take the first equation and we're going to leave it as is, because that first equation resembles my target equation in that it has graphite on the left side of the equation. That's what I want. The second equation I'm going to manipulate. I'm going to reverse the second equation because in that second equation, I see that the carbon monoxide is on the left side, but I want carbon monoxide on the right side. So I'm just going to flip it. But when I flipped that second equation, I also had to flip the sign for delta H. And so now instead of negative 283, it's a positive 283. Didn't do anything to the first one, so I'm going to write its energy right back down. Okay, couple of quick notes. You'll notice that we have delta H not of reaction. Remember that not, it means that we are at standard state, which for gases is 1 atmosphere. And then again, please note that I changed the sign on that second equation because I flipped it around. If we now add these two equations, and we will find that we have our overall target. So let's do this. So what I've done right now is everything that was on the left side of either of those two equations, I've written on the left side of my overall equation. And everything that was on the right side of either of those two equations, I've written on the right side of my overall equation. If we now treat this like a math expression and I look to see what's on both sides, I notice that I have oxygen on the right and oxygen on the left. This half a mole of oxygen on the right will cancel out half a mole of oxygen on the left, and so I'm left with only half a mole of oxygen. I also notice I've got CO2 both on the left and the right, so that's going to cancel out. What remains is my target equation. So I can add my equations now once I've manipulated them. And just like you would add the equations themselves, you're going to add the values for delta H. So I'm going to take negative 393.5 and I'm going to add to that 283. And I'm going to find that the standard heat of reaction for this process is negative 110.5 kilojoules per mole RXN, so as written with the coefficients in that equation. Okay, a couple of tips as we're looking here. First off, the equations I'm giving you will always work. They will always be able to be manipulated and add up to your target equation. So start by looking at your target equation and find each of the chemicals in the equation and make sure it's on the proper side of your equation that you're manipulating and that it has the right coefficient. Change those if they don't, and then you can add everything up. Let's do a more complicated one so you can see how that works. Okay, so for this one, we have 3 equations that we are going to manipulate in order to allow us to calculate the heat of reaction for ClF as a gas plus F2 as a gas, forming Cl3F3 as a gas. When I look at this, I am going to note that I need to get 1 mole of ClF on the left side of my target equation. Looking up to the 3 equations that are above, I find ClF in the first topmost equation, but it has a coefficient of 2. It's on the right side, however, or on the proper side. So what we're going to do is we're going to take that topmost equation and we're going to multiply by a half. So we'll carry out half of what's written. And since these are moles of chemicals, you can totally react half of what you started with. So I'm going to take that first equation and I'm going to rewrite it with everything being half as much. And when you have half as much of all the chemicals reacting, you'll get half as much of the energy being transferred. And so now I've manipulated to get me the first of my target chemical compounds. Let's do the second one. So I want to get 1 mole of F2. Looking at the equations up above, I see that this third equation has the F2 in it. But again, while it is on the proper side of the equation, it does not have the right coefficient. So I'm going to take that third equation and I'm going to multiply everything by a half. And when I multiply the equation by a half, I multiply the value of delta H by 1/2. Okay, and then in my target equation, I need ClF3. I find ClF3 right here in the second equation. It has the wrong coefficient and it's on the wrong side of the equation. So we're going to flip this equation and multiply by a half. So let's do that. And when we flip and multiply by a half, I'll do the same thing with my value for delta H. So instead of 341.4 kilojoules per mole, this is now negative 170.7 kilojoules per mole. And so now as I look at this, let's make sure everything adds up. Again, let's take everything that's on the left side of the arrows and put it on the left side of my overall equation. So I have CLF. For the O2, it turns out I have O2 in two places. I have it in the first equation and the second equation. A half in each makes for 1 mole of O2. And then we'll do the same thing with the product side. And here again, I've got half a mole of F2 and then another 1 mole, so I'm going to make this 3/2 moles of F2O. And then once we've done that, we're going to look for things that are both on the left and the right side that we can cancel out. I see 1 mole of oxygen gas on both the left and the right side. Similarly, I see 3/2 mole of F2O on the left and the right side, and half a mole of Cl2O on the left and the right side. And yes, folks, what's left is our target equation. So we've now confirmed that all of our manipulations worked, and so I can just add up the modified values for heats of reaction for these three equations. And when I do that, the overall heat of reaction turns out to be negative 108.7 kilojoules per mole as written. And so by manipulating a set of given equations, you can predict the heat of a reaction for an overall process.